Good evening and welcome to RASC Toronto Centre Online. I'm Dr. Elena Hyde, and I'm the second vice president of the RASC Toronto Centre, and this is our May Speakers Night presentation. So as some of you probably already know, this is one of two types of gathering that we have online these days, not at the Ontario Science Centre, unfortunately, due to that pesky pandemic. Our president, Tom Luton, will be talking about our various programs later on this evening, but first, we do have, of course, a very special event tonight to kick us off with all kinds of exciting, we'll find out. For our speakers night tonight, we are delighted to welcome Dr. Claire David from York University's Department of Physics and Astronomy. And I, of course, have the wonderful task of getting to introduce this fabulous speaker to you all. So Dr. David's first degree was actually a Master of Engineering in Applied Physics in France, specializing in nanophysics and instrumentation. And she has, as you will find out, switched gears towards more fundamental science since then. She obtained her PhD in experimental particle physics from the University of Victoria, working in the ATLAS collaboration. She has then, of course, continued working with ATLAS and as a postdoctoral fellow in Germany, and she now is an assistant professor at York University, jointly appointed, I believe, over at Fermilab. So very, very exciting. Her research is on the subatomic world, so very, very, very tiny things we'll probably be hearing about later, split between collider physics, so, a pun intended, and neutrino physics. She is starting the new Canadian effort towards future Deep Underground Neutrino Experiment, or DUNE, which is hosted by Fermilab. If you want to find out more about her, make sure to check out her new webpage on yorku.ca/science/Claire David. And since our speaker tonight is so, shall we say, particular, I thought our folks in chat might get a little bit of a kick out of this particular joke to start us off. Why is a neutrino the worst to go on vacations with? And I don't know if I should give a second for people to go ahead and guess, but it's because it doesn't make any stops. So feel free to try that out on your favorite person to tell jokes to. So without any further ado, Dr. David, please show us how to get through this topic and take it away.
Hi, hello everyone. Thank you so much for having me. This is really a great pleasure to be able to talk about DUNE, the Deep Underground Neutrino Experiment. So DUNE is a big project, a huge facility, an international endeavor. And I'm going to take you on a journey, and thanks Elena for the joke, and we will take on a journey where we'll make stops so that you will understand step by step what's going on. So embark on the underground telescope to pierce the secrets of matter. And I'm going to start with the following view that as astronomers, you may be keen to see. This is our universe. This is a picture showing galaxies and visible matter. And this is quite wow, I would say, to be able to see this as a species and trying to understand our universe. And my specialty is particle physics. That is to say, I want to answer this question: what is the universe made of? Through the tiniest pieces of matter. So matter is organized. We've known this for more than a centuries, and even there were hints of organizations really earlier in history. And what we have when we zoom in on matter is that we have a structure. If we zoom, we have what we call an atom, and this may be familiar for some of you, totally new for others. So an atom, this is a structure in the subatomic world, subatomic, that is pretty much take a millimeter and divide it by 1 million, and this is pretty much the size of an atom. This is very, very, very small. An atom could be seen like a planetary system, although it's not actually the case. It's a bit more fuzzy, but you could represent it approximately with a nucleus at the center with electrons orbiting around this. Electrons, you may be familiar with this particle. It's been discovered in the early 1900s, and all of these electrons orbit around that nucleus. And this nucleus has also a structure. It's made of different subcomponents that we call nucleons, and you may have heard of protons and neutrons. And these protons and neutrons, if you open the box or try to see inside them, they are also composed of other particles that we call the quarks, and they come into different colors in the theory of particle physics. We will see this soon. Where I'm interested in as a particle physicist is basically the elementary particles. What we can't really go further when we zoom in, that's it. We have a point like objects. It's quite of an abstract concept if you think of it. So basically my job is to play Lego with the tiniest Lego you can find, the building block of the universe. They are the bricks, that's the building block of the universe, and we particle physicists, we studied them, and we also want to know how they interact with each other. And the way that we see these interactions, we see them through forces. You are surely familiar with electromagnetism, electricity, magnetism. This is combined into one single force. That is the lightning and magnet, but also the fact that matter is just there. You can't really go through matter because of the electromagnetic force just holding things together. Then the weak force is the force that is responsible for radioactivity processes. It's involved into all of the decays of elements. And finally, the strong force is what is very strong at very tiny distance to be able to glue all of the quarks together inside and forms the neutrons and the protons. Gravitation is not included in particle physics. Einstein tried and he failed, and we're still at it. At least we have a way to unify this, to have these three forces well defined in our theory. Talking about the theory, in elementary particle physics, the people previously, very brilliant minds, have thought of nice theories. I put the equation at the background. This is for decoration. Don't freak out. This is a beautiful endeavor and realization and achievement that is our theoretical models to be able to describe all of these elementary particles of visible matter and then the interactions that are in between them. And we call this the standard model of particle physics. And I will describe it a bit in here. We have on the left, all of here, you can see my cursor. These are the bricks of matter. And here we find the electrons you're pretty familiar with. And the electron has a cousin, heavier cousin, 207 times heavier, that we call the muon. And there is even another heavier cousin called the tau. These in the columns here are called generations of particle. The first generation is the object we're most familiar with, everything that you're made of yourself and you see. But at higher energy levels, you can produce these particles from the higher generations, and then they will decay back to electrons, for example, for these ones. These are the leptons. The neutrinos, I will go back to them later because this is the topic of this talk. So I will do a tour of what is other than the neutrinos. So here we have the quarks, as I told you before. These elements are there in forming the nucleus of atoms. And if you want to make a proton, for example, you will take 2 quark up and 1 quark down. If you want to make a neutron, you will take 2 quark down and 1 quark up. That's the recipe. That's it. You can make a universe, pretty much. But the quark charm strange are heavier cousin of these up and down quarks, as well as the top and the bottom. These are part of the third generation. On the right, we see the particles that are message carriers. They are responsible of the forces, and you can imagine them being exchanged during interactions. We have the photons, which is a grain of light. That is it's being exchanged during electromagnetism. Then these W, Z0, W minus, these guys that are bosons, they are bosons of the weak force, and they are involved in these radioactivity processes that the weak force is about. Last but not least, we have here the gluons, and the gluons are exchanged between quarks, and as their name indicates, they are basically binding the quarks together. So that we have neutrons and protons and entire structure regarding matter. Now you may wonder what is the dot in the middle, the Higgs boson. I think this is the topic of a talk, so you can re-invite me and I'm happy to talk about the Higgs boson. Short story, because tonight is about neutrinos. The Higgs boson is a particle that is interacting with other particles that are massive to give them their mass. Basically, all particles are massless, and the Higgs boson is the element, a bit like molasses, that are going to slow down particles that are more massive, and the more it slows down, then the slower the particle are, and this is interpreted as the particle being massive. So that has been discovered at CERN in 2012. Actually, I was there during the announcement of the discovery. So I've seen Peter Higgs, but I haven't seen, I've seen the Higgs boson indirectly into the data. And that was quite a big discovery. And that got me thirsty about more discovery. So here we go with the neutrino, because with the neutrinos, there is a way to discover a lot of things. Elena introduced them with a nice joke. I would say neutrinos are antisocial and moody. So that's still not qualifying to go on vacation with, right? So why are they so? A bit of explanation. So first, antisocial. Neutrinos are barely interacting with matter. Basically, they go through, they're not polite, they don't say hello. Right now, you have gazillions of neutrinos that are going through your eyeballs, coming from the sun per second. Yes, that's something like 200 billion neutrinos every single second going through your eyeballs. And don't worry about eye dryness and so, because they just don't interact. They go completely through matters. And you will see it even more on the next slide, because every second, a little piece of 1 square centimeter on the surface of the Earth is witnessing 65 billion neutrinos going through it in the direction perpendicular to the sun. Now, hold on. This is almost the same number in the reverse on the other side of the Earth. So basically, most of the neutrinos are going through our entire planet without interacting with any single atom of the rock of our planet. That's how antisocial they are. So now, before I introduce their moody aspects, I would like to get you a bit acquainted with what are the different sources of neutrinos. So we have the sun, as I told you, and I put at the bottom some formulas for people having a scientific background if they want to know a bit more. The sun is producing a lot of neutrinos. Then we also have atmospheric neutrinos, and this is important for DUNE, you will see soon. When you have a high energetic particles hitting our atmosphere, then it will, what we call cosmic rays, it will, after the crash, produce some neutrinos, and these neutrinos are flooding our surface, and they're also harmless, and they are irradiating the lower layers of atmosphere and then us. They come from cosmic rays, high energy particle hitting our atmosphere. There are other sources also of natural neutrinos, but I want to point to the man-made neutrinos. As soon as you build a reactor with the nuclear fissions and then what we call beta decay, you're making neutrinos. And actually, a lot of neutrinos are being studied next to reactors. Last but not least, what we'll see in this talk is that if you have an accelerator complex, then you can make neutrinos, and you can actually make quite a lot of them. And this is what Fermilab is going to do for DUNE. Stay tuned. Okay, a bit of a history now, because I want you to understand how we managed to detect that particle that is just so antisocial. It all started in 1930, where physicists had a problem. As soon as physicists had a problem, surely enough, there would be a discovery. So keep it also as the philosophical quote of the day. If you have a problem, you may discover something soon. And the problem was of energy conservation. In physics, if there is a law that is really there all the time, is that energy is conserved. You have energy in, energy out, that should equal either mechanic, bit of heat out and so, but if you do the sum before, sum after, it should match. And it was not matching in beta decay. What is beta decay? Where the nucleus is just transforming into another element, it spits out an electron. So we can measure the energy of the parent, and we can measure the energy of the daughter particle, that's how we call it, and the energy of the outgoing electrons. And we realized that it was not matching. There was an imbalance of energy. To solve this, physicists postulated, they just thought there should be actually another particle that is neutral, that is barely interacting with matter, but that carries actually this little energy missing. So then after we can have an equal sign and we're all happy and we celebrate. The person that thought of it first was Wolfgang Pauli, a very important physicist in the establishment of quantum mechanics. And he hypothesized the existence of the neutrino, and there is a famous quote associated to it: "I have done a terrible thing. I have postulated a particle that cannot be detected." Imagine the atmosphere at that conference when the old physicists realized that. This being said, they didn't give up. Actually, a very famous physicist, Enrico Fermi from Italy, and the Fermilab bears his name, he actually thought of it, and he is the one who named the neutrino as the little one in Italian. And he proposed a theory called the Fermi interactions, where the neutrino was completely included in it, and he tried to publish a paper about it. And that paper was rejected by Nature, the prestigious journal, stating because it contains speculations too remote from reality to be of interest to the readers. Bummer. Okay. But still, there were people thinking perhaps we can detect that things. It's good to see the immense amount of hope and tenacity among some physicists. And two of them, Frederick Rains and Klein Cowan, did this. In 1956, the neutrino was discovered. They were next to a reactor. That's a good source, the Savannah River plant, and they built that detector that managed to produce some signals that was a clear indication that the neutrino was there. And this is not all. Remember the Moody? People studied the properties of the neutrinos, and right near their assumption, when people were right after the discovery, Bruno Pontecorvo, another theorist, was thinking that perhaps the neutrinos present in different types can switch types and to another when they propagate through space and time. And this switching of type is called the neutrino oscillation. That is a key aspect of this subatomic particle. And this has been confirmed. This has been confirmed really quite later, really later, whereby these two Nobel Prize winners, Takaaki Kajita and Art McDonald. Art McDonald is Canadian. He was the SNOW experiments, and they won the Nobel Prize in Physics in 2015 to show that neutrino oscillations happen. So what are neutrinos oscillations? Okay. Neutrinos, they come into three flavors. Think of it as costume. The electron-neutrino, the muon-neutrino, and the tau-neutrino, like the lepton that I introduced to you before in particle physics. So these three neutrinos are actually what we detect when we interact, as if you're in a fashion show and then you see the person with a costume. You don't see what's behind it. You just see the costume. Turns out that neutrino will change flavor over time, and there are two ways to see neutrinos. We have what we call a mass basis. Think of it as the model carrying the costume. We don't really know them, but they will have a mass, a different mass, so M1, M2, and M3. And this is when they propagate. This is when they go from traveling distances through time and space. Okay, and then we have what we call the flavor basis. When we just take a camera and we detect a nice costume, we can actually see electron-neutrinos, muon-neutrinos, tau-neutrinos. Turns out that there is no correspondence between 1, 2, 3 and electron, muon, tau. There is what we call a mixing. In quantum mechanics, we call this a superposition of states. We just have all of this mixing, and then we have a probability to observe one, and then so, yeah. So what is happening is a bit like the sound when these neutrinos are mixing. So I'm going to play some sounds. So the sound one is this. Let's see if it works. It worked before. Okay. You see it, right? Now, this is the sound 2. You can barely differentiate this, right? This is 44 hertz and 4041, pretty not differentiable. Now I'm going to mix the sound 1 and 2. Listen carefully. Okay, could you hear this? Right? We have actually beats, some sounds and then no sounds, and sounds and then no sounds. This is because the waves in here are going to superimpose, and here we see that they're on top and then also top and top, so they're going to amplify, but at some point the waves are going to cancel each other, like in here. So we have basically sound and no sound, and sound and no sound. So this is the exact same that is happening at the quantum level with our neutrinos. we have this nu 1 and nu 2. So this nu here, the letter that I call nu, this is the Greek letter that is symbolizing the neutrino. It really looks like a V, but it's actually nu. And physicists learn very early to differentiate the Latin and Greek alphabets to be able to name things according to their conventions. So these neutrino 1, neutrino 2s are traveling at different phases, different speeds in time and space. And then in here, you can see that if its neutrino happens to interact, there will be a pure muon-neutrino flavor. And then at some point up, we will have an electron-neutrino. So we will have an appearance of a different type and then disappearance, and an appearance again, and then disappearance. And we managed to compute the probability for a given flavor with a given initial energy to know actually how likely it is to observe this flavor after a given distance that has been traveled. That is pretty amazing, I would say, to be able, out of a particle that is barely detectable, to know that not only we detect it, but then we know how that changes some costumes, and we know actually the probability of some costume observation. Great. But there are lots of things we don't know. Neutrinos are pretty enigmatic. The first thing we do not know about neutrino is why they are so damn light. They are very light. A way to picture things is that I'm going to put all of the neutrinos on the scale. This is a mass scale, so we use this EV, that is our unit of mass in particle physics. So kilo EV, and then mega 1 million, and then 1 billion, and then tera electron volt. Think of it as normal objects. If, let's say, 1 EV are as heavy as 2 grains of raisins, dry raisins, then you will have a laptop that will be 1 kilo electron volt. And all of our particles will be just at very different masses, like spanning 6 orders of magnitude. And the biggest one would be as heavy as a plane. And I put an A380 because this is the plane that was built in my hometown anyway. And then the neutrinos are just there, super light, like in this comparison, that would be the weight of the mass of a mosquito. This is puzzling physicists. We want to know, why is it so? And then which neutrino is the lightest, which neutrino in the heaviest, we have no idea. We know that there is neutrino 1, neutrino 2, neutrino 3, and we don't know if the masses are 1, 2, 3, or if the masses are 3, 1, 2. This is called the mass ordering, and this is completely unknown at present time. And then the mechanism that is giving mass to neutrinos. I told you about the Higgs boson. This is here, this makes no sense. The neutrinos in the model of particle physics are supposed to be massless, and yet they have a mass. So we have no idea what mechanism is giving neutrino their masses. Another dark area of question marks that we have in physics is, are neutrinos oscillating the same way as antineutrinos? Matter is always produced as matter and antimatter, the same way as if you do a confetti, you would just pinch, you would have your confetti and you would have the whole. This is how matter and antimatter works. They recombine into some lights. And for the neutrinos, we do not know if neutrinos and neutrinos are actually oscillating the same way. And that has big implication for our entire universe. I find this fascinating about neutrino physics, is that studying one particle gives you hints on our entire cosmos. I am quite baffled by this. So yeah, after the Big Bang, there should have been an equal amount of matter and antimatter created, complete symmetry, and then everything recombines into lights. And we are not there to talk about it. Turns out that a tiny more amount of matter was produced over antimatter, and basically the surplus that has not recombined is our entire universe of matter today. Crazy, right? We don't know why, and perhaps neutrinos could bring some hint with this if we study how neutrinos and antineutrinos are oscillating. Okay, now in astronomy, cosmology, you may like this, what happens when a star dies? You may have heard of this big phenomenon, huge explosion that is a supernova. If a star is heavy enough, it would just, at the end of its life, fall into itself and then explode. And what is released actually through this huge burst is pretty much neutrinos that will actually carry 99% of the energy. This being said, the total mechanism of what we call core collapse supernova is quite unknown. This is a big problem in astrophysics. We want to know more on this. And again, neutrino may bring some answers. Great. So now you're pretty curious on what kind of answers we're going to bring. Well, for this, first we need to build an experiment. In particle physics, experimental particle physics, there's a lot of thoughts and studies and head scratching and brain juice into designing an experiment that can bring answer on a particle that is so antisocial and moody. And this comes DUNE. DUNE stands for Deep Underground Neutrino Experiment. This is a complex of detectors that will be located partly one in Fermilab, that is the host lab, and in a laboratory in South Dakota called the Sanford Underground Research Facility. And in here, if you wonder how big this tunnel is going to be and how nuts it is to dig into the Earth, remember the slide before when neutrinos are going through the Earth? At least here, neutrinos make it easy. We do not have to dig a tunnel. We just shoot a beam into the Earth, and then the neutrino will travel as long as we align the beam properly. So here is an introduction to the type of detector that is DUNE. DUNE is a long baseline neutrino experiment. What does that mean? It needs three ingredients. It needs a beam, and there will be a big neutrino beam. We'll just cover this in a second. Once the neutrinos are produced, then they go through a detector that is near the source of near the beam, and this is called a near detector. No kidding. And then the neutrinos are traveling through the Earth, and this distance of 1,300 kilometers is not by chance that we came up through it. It's because then we'll actually give time, space and time for the neutrino to oscillate properly, so then they will show up with another costume on the other end. On the other end is where we have the far detector, because it's far, and this is the detector that is really deep underground, and we will see why. And all of this complex in here will allow us to be able to study neutrino properties and see actually how the oscillations happen between neutrinos and antineutrinos, along with many other studies, so that we know more about other neutrinos properties, as well as some candidate theories of non-standard neutrinos, etc. Huge physics program. That is the DUNE detector. And for this illustration shows you that over the distance, if we start from a given type of neutrinos, like let's say a muon-neutrinos, after some distance when the neutrino travel, there will be other flavors appearing, and then we'll be able to basically count the different interactions of the different costumes of these neutrinos before and after, and that will really bring our key answers for the questions that are still puzzling us as physicists. Great. Now I will show you a video of Fermilab. This is
Fermilab, a Department of Energy national laboratory near Chicago. And it's the starting place for the Deep Underground Neutrino Experiment, DUNE, powered by the long baseline neutrino facility, LBNF.
The DUNE experiment. Everything will be starting in this facility that you can see here, where protons are going to be accelerated. Here there is an accelerator that is going to be actually upgraded. This is a big project that is undergoing at the moment to be able to produce the correct energy of all of these protons that are going to fabricate the beam of neutrinos. And here it is. They will go on a little hill that you can see in here, right? And this is where they will be pointed down towards South Dakota, and then they will hit a target, as you can see. And once they hit a target, other particles are produced, and these particles decays, and then they produce neutrinos. These neutrinos are going through the near detector, as you can see, and then data is being brought to the surface so that we can study. Then the neutrinos are taking their journey through the Earth, and they will hit the far detector. Not to mention that if we happen to have a supernova exploding in our near Earth, we will be able to actually detect such neutrinos produced by supernova. I will end my talk this way. This is how the far detector looks like. It's a huge tank filled with a special element called argon, very cold, it's liquid. And then once the neutrino interact with this liquid, they will produce some charge. And this charge are going to be drifting away because of a strong electric field, and they will be picked up by electronic. We'll see this later. Then the data will be sent towards the surface. And as we'll have an enormous amount of data, something unprecedented, we'll actually need an entire system of large-scale computing to be able to analyze it all and then infer and answer the questions that we are looking for on how neutrinos behave. Okay, now a bit more on the elements of DUNE. Let's start with the beam. This is quite fascinating. So the beam is produced by a special facility that you could see in the video, that it's called the Long Baseline Neutrino Facility, LBNF. It will help DUNE get its intense neutrino beam, actually it will be the most intense neutrino beam in the world. And the protons will hit the target at every 1.3 seconds. And this power that is associated with this is 1.2 megawatts. Then before they hit a target, actually, you will have to orient the protons because neutrinos have no charge. It's impossible to direct them. So we direct the beam of the protons in here to point to South Dakota at minus 5.8 degrees. And this is what this hill is doing this. So then after the beams are hitting the target, the neutrinos are correctly aligned, more or less. When all of these protons are going to hit the target is going to heat up quite a lot. The target is actually a 1.5 meter long rod of graphite, and graphite behaves well in here as a target in that purposes, but it's still going to go to up to 500 degrees Celsius in a few milliseconds. And you can't really cool it down with standard methods because this is a target being just having tons of protons hitting in it. So what we will do is that we will use a gas system of helium at a huge, insane speed. So think of an aircraft taking off 720 kilometers per hour. That's pretty much how fast that gaseous helium is going to flow through the target so that the target doesn't get too warm. And last but not least, I will introduce you to the focusing horns. What is this? When the protons are hitting the target, there are these particles produced that we call pions and also kaons. And so these particles are charged and they're going to decay and produce neutrinos in the process. But as they are charged, they're going to really spread as if you have a jet or a shower. It's conical. We want to focus this. This is where the focusing horns are just coming into play. These elements here are going to squeeze the beam so that it really keeps its directions and it's very nice and narrow towards South Dakota. And these horns, to be able to work, we need actually a pretty strong current going through the horns to be able to be so that the focusing happens. And this is the picture of what we call the strip lines. These metallic structures in here are the one where to be plugged with an enormous generator where 300,000 amps are going to go through to be able to get the horns doing their jobs of focusing. So 300,000 amps in terms of current, this is comparable to a lightning. This is what is needed to be able to focus the most intense neutrino beam of the world towards the detectors of DUNE. Then come the DUNE's near detector complex. It's actually collections of different detectors. One is a beam monitor to be able to study the beam. And then there are different complementary sub-detectors that could be actually put outside of the beam or back on track on the neutrino beams on demand, so that only the beam monitor is doing its job, and then we can just insert the detector and so. And the near detector is pretty much a project on its own because it has also its own physics program to have more measurements of neutrinos, to understand more neutrinos interactions, and to search for non-standard neutrinos that are not yet in our theory, but could perhaps explain what we don't understand yet. This will be a challenge because as it's very near to the beam, it's going to have lots of interactions per microsecond. So this is the whole technologies of neutrino detection has to be rethink so that we have electronics fast enough and a readout system good enough so that we can understand all of the signals coming all at once. Then our neutrinos are going through the Earth to reach the far detector. And this will take 1,200 kilometers. And this will go very fast because neutrinos are really, really, really fast going particle. Now comes the DUNE far detector. This is located in South Dakota into an old mine. And this is 1.5 kilometer underground. This is very important. Remember the source of neutrino? I told you about this cosmic particle hitting the atmosphere and producing neutrinos. We are flooded with these neutrinos that we don't want. They are not the one coming from the beam. So we need to shield from it. And the way to shield from it is to go really, really deep so that all the things that are just hitting us on the atmosphere, it's just not going through. And then we'll be able to have a clean environment free from cosmic rays, neutrinos, so that we'll be able to see only the neutrinos from the beams and also from the cosmos that are happening at a different energy. So then DUNE will be able to see them. What is the 4 detector made of? Then this will be this huge caverns excavated, welcoming modules. And modules is depicted in here, and we will see it into the next slides. It's going to be the largest cryogenic instrument ever, 89 kilotons. I will explain you later. And this is going on the technology that we call the liquid argon time projection chamber. This is a pretty well-proven technology in neutrino detection that is very powerful because it can actually bring pictures of neutrinos interaction with a very nice resolution. So think of it as a high-def picture. And as I told you, neutrinos are antisocial. So usually if you want to make a swimming pool so to have a chance of neutrinos to interact with the liquid in the swimming pool, you rather scale it up. And this is how one module will be. You have a human in here, 66 meters long, 19 meters wide, and then 18 meters high of a fancy tank. Don't tell my colleagues that I call this tank. It's a fancy tank, okay? And this huge swimming pools for detecting neutrinos is filled not with water, but with a heavier element that is called argon. And argon have a lot of interesting properties when it comes to neutrino detections. And the one module that you can see in here will be filled with 17,000 tons of liquid argon that is cooled at minus 184 degrees Celsius. And that would be our swimming pool for neutrinos. How do we detect neutrinos in that swimming pool? They are going to be this is the view side on one of this module. If you actually look at this way and go inside, there are these huge panels in here made of wires. And these panels are going to have an electric field, a very strong electric field horizontally between them, so that as soon as a neutrino will interact, it will produce some charge and they will drift towards these panels and they will project a neutrino interaction. What do I mean in here? A video is going to illustrate this for you. Once you have an incoming neutrino reaching the liquid argon swimming pool, if it interacts with an atom, light is produced and then charges are produced. We have a proton and a muon being produced through that interactions. As they are charged, they produce some electrons that are drifting along the way, and these electrons are going to hit the anode, and these anodes made of wires are going to pick this up as an electronic signal, and we can after reconstruct these events. This is how a time projection chamber works. And if now you may be curious, okay, so I've seen the video, but how does it work in real life? Can I see real pictures of neutrinos interactions? Actually, we can. For this, we will take a little detour. Let's cross the Atlantic, go to Switzerland, Geneva, CERN, the European Center of Nuclear Research, a particle physics lab that is where the Higgs boson has been discovered. And I've been working for CERN in the past 10 years. CERN has made within quite only 2 years a neutrino platform and has built actually a mini DUNE. This mini DUNE is a prototype. It is actually called Proto DUNE. And this is a demonstration, a way to know if it's possible to have this liquid argon time projection chamber technology at large scale. This, even if this is not the DUNE dimension, this is 11 by 11 by 11. This is still the largest liquid argon time projection chamber we ever built. And it looks like this. Seen from the top, you see one prototype of Proto DUNE 1 and then Proto DUNE 2. And if we see it with this cartoon, you can see that the planes in here that we call anode plane assembly and then cathode plate assembly, this will be exactly the same, just longer and bigger in the real DUNE 4 module. And the Proto DUNE is reproducing and studying this using CERN's beam. In here, you can see the beam window. To give you an idea of the size, this is a human being next to one of these anode plane assembly, and you have 6 in here. Look at my cursor. This is 1, this is 2, and this is 3. And then with these planes that are cabled with a lot of wires in here in different directions, it would be possible to pick up any neutrino interactions and particle drifting from the product made by a neutrino knocking an atom of argon. And this is depicted in here with this animation. If you have an interactions and particle drifting because of a huge electric field, they will create signals. This is the time. This is what we see actually according to time. There will be these little bumps that each different wires are going to bring. And as there are lots of wires, we can actually reconstruct all of these bumps and be able to have a 3D picture of a neutrino interactions. This is a picture of Proto-DUNE. Proto-DUNE was running in 2018 and brought us the first pictures of a precursor of DUNE, where you can see in the different planes of the wires are aligned this way vertically. And what you can see in here, so this is wire 1, wire 2, wire 3, from all of these wires in there. And vertically is the time. So this is, if you're in here, you see it at t0, and then you just increase in time to see your interactions. It's difficult to picture actually this in 3D. This is a time projection in the wire number and then the time components. To be able to have a 3D model, we need a lot of algorithm cleverly done so that we bring all of these data, all of the times, all of the wires, as well as the photons. Remember in the video, there were photons produced. These are actually telling us, oh, an interaction is there, called the trigger. They make sure that we record everything so that we can see if we have a neutrino interactions or not. All of this is combined together, and here we go. We can have a very nice 3D picture of our neutrino interaction, as you can see it in here. We see here the interaction of interest. This a neutrino coming from the beam, CERN beams, that is interacting with argon and then has produced a shower and then other particle. And this is one interaction we store and we'll collect a lot of them and then study them. They are interaction for cosmic rays. See the tracks appearing in here? These are the noise, the shower of cosmic rays from the atmosphere that we have and we want to get rid of. Proto-DUNE is in the surface. DUNE will be deep underground, so at least we will not have these noisy tracks. Right now, there is construction at the 4 detector sites at the South Dakota, and we're in 2021. Things are going well. There is excavation going on, and we'll try to make all of the caverns that will host the DUNE 4 detector modules. These modules will be just brought by stage, so that we will test one and then another will be installed, but in the end, 4 modules will be there into making the 4 detector. It will start in 2029. These DUNE operations will go up to 2036. And even after, even if the detector is not working anymore, there will still be some years where physicists will be busy to analyze the data. And a lot of things will be going through the data. Last but not least, as I told you, DUNE will be sensitive to not only the beam neutrinos, but the neutrinos coming from the cosmos. In the night of February 23rd, 1987, there has been a big supernova that was observed by neutrino observatories, and the neutrinos of a supernova can reach actually 2 to 3 hours, sometimes days, before the light comes in. This is very valuable. And the thing is, we had only that supernova, so that's not stuff to study. And right now, we still do not know how a core collapse supernova is working. There are models, we can expect things, but we would like to confirm them. Supernovas can happen within 30 years, 200 years. So we really would like to have DUNE switch on, and then we see and try to record the details of a supernova and the neutrinos coming from it. Supernova is a huge explosion. This is 10 to the 58 ergs. Ergs may not ring a bell, and it's fine. I made a comparison for you. Ergs is a unit of energy. There is another unit of energy that is the TNT equivalent. TNT, the explosive. We can talk about megaton of TNT, let's say, for very energetic events. Hiroshima and Nagasaki, the 2 bombs combined, are 0.035 megaton of TNT. A supernova, a core collapse supernova, represents an enormous amount of energy. We have here 24 billion megatons of TNT. This is insane, and I don't think that any human being can picture such an explosion. only a very few percent of this energy is carried by light. 99% of the energy is carried by our neutrinos. Think of all the valuable information they can bring to us. So this slide is a bit technical, but I want to show you what we expect. We expect within some milliseconds a huge spike of some neutrinos of different flavors. That's the step of neutronization. And then in less than 1 second, we will have also other neutrinos coming in, having a very clear signal according to the latest models, to the latest prediction. And then the cooling will happen, and between 0 and 8 seconds, we'll see such trends on the number of neutrinos that will be coming from the cosmos. If we see a sharp drop, for example, that could hint on some black hole formations, and that would be actually a witness in astronomy using neutrinos to be able to understand and to see how at some point a black hole has been formed. And how we could see neutrinos in DUNE? Well, when neutrinos coming from supernova are hitting argon, they will produce specific elements, excited elements that are going to actually release a photon, a grain of light, into a specific color. And this specific color, this is what we're after. This is why we can see, oh, these neutrinos are coming from a supernova. And we'll see a lot of them because it will be a wave of these neutrinos coming in and passing through the detector. There is another interaction happening where the neutrino is hitting one of the liquid argon electrons. And basically we'll see an electron being just kicked and being what we call scattered. And this is something we can pick up as a signal in DUNE. So DUNE, being able to see supernova is something incredibly exciting. It would be, though, a huge challenge, because then we will have an enormous amount of interactions per second that we'll have to deal with. So this is really requiring the electronics to be fast enough to be able to register all of these signals on time and store it there as data that we analyze later offline. This requires also a special trigger system, because even if this explosion is enormous, once the neutrinos are reaching us, this is pretty much low energy. So this is really trying to detect the smallest wave into a sea that sometimes will actually be wavy to start with, to see if this is noise or if this is actually a signal. So there are intensive studies on a trigger development for this supernova detection. Last but not least, if there is a supernova going through the DUNE detector, the amount of generated data is going to be huge. It's going to be in the order of 100 terabytes in 100 seconds. So this demands a computing infrastructure that is able to deal with this. You do not want to have a Niagara and then having a straw and trying to see, oh, it's going to be fine. It's going to be enormous. This being said, it is so incredibly exciting that DUNE can be part of what we call multi-messenger astronomy, where actually it could warn for a supernova coming and tell all the friends and telescopes, please align into that direction. Because yes, DUNE may be able to determine where is this supernova if it detects it, and then it will warn the others to be able to then have a nice paparazzi show on a supernova exploding. And I found this very, very exciting. Thank you very much for your attention. This was my little journey on DUNE as a neutrino astronomer.
Well, thank you very much, Dr. David. I think you've certainly helped me and a few others maybe feel like we really matter, so to speak. This has been a wonderful journey with lots of interesting stops on the way, a bit of a mini vacation almost, combining the largest and the smallest scales. I have to say I really love the picture you painted of this fluctuating costumes changing by being worn by unknown masses. I have to be honest, I was thinking about including a speed of light joke here at the end, but like in your supernova, the neutrinos beat me to it. We've got some questions coming your way, however, and I think we've got, oh gosh, probably about 10 minutes or so. So I am going to go ahead and pass over to Emma for questions for our speaker now. Emma, take it away.
Hi, we've got some really great questions tonight. First question, would the existence of a multiverse alter the standard model?
Ooh, That is starting well with the question right away. Actually, I will do a very biased answer as an experimental particle physicist, in the sense that I'm interested in understanding this universe with the things we can measure, we can access to. It goes a bit contradictory with what I said before, where the neutrino was postulated with pretty much no way to detect it. But in the multiverse theory, which I am not an expert in, this is something that is quite very, very tricky to measure. So perhaps there could be some portals, perhaps there could be some ways to link with this, but so far, I would say tricky to be able to infer in here.
Thank you. Do neutrinos interact with each other? They don't interact with other particles, but how about each other?
Be caution with the neutrino self-scattering. We are talking about someone extremely antisocial interacting with someone extremely antisocial. Good luck. Neutrinos interact a lot via the weak, the bosons of the weak force. This is where they are mostly interacting, and they are, we talk about charge current interaction, neutral current interactions through the bosons of the weak force, and the neutrinos are only interacting through that weak force.
Thank you. Will the new fusion reactors also generate neutrinos?
Oh, good questions. I would say it's a bit unavoidable that there will be some. Actually, I don't know how exactly it compares with the fission reactor, but perhaps I'm going to ask a question. Will the fusion at some point happen? I don't know.
Yeah. Have you worked at SNOLAB?
I haven't worked at SNOLAB. I would like to go at some point. I've worked at CERN, Triumph, and at DESY in Hamburg, and also in Berlin. So not there yet, but one day, perhaps.
One day. With DUNE covering such a large path, do you have to monitor the Earth for activity like earthquakes and volcanoes?
They will not be so much different, because as I told you, with the beam, it's going to burst every 1.3 seconds. So in the end, we're going to have a pile of data of all of these bursts and all of these interactions. And if at some point there were perhaps an earthquake or even something very big, I don't think an earthquake can actually infer. The neutrinos is antisocial, as I say. But even it's going to average out, because we'll have a collection of many interactions through all of these beam bursts that are going to be sent at regular intervals, and then we'll just collect the data through it.
Okay. How wide does the neutrino beam get?
How wide? Oh, this is a good question, but I would say that this is something we can't really measure per se. We will only focus as much as we can, and it would be said when we would have the detector there, and then we'll be able to measure and to see if we expect the neutrino according to their relative abundance, but this is something that will spray as a cone, because you can't really avoid and have a very perfect beam. So this is going to be definitely wider than the size of the DUNE detector. So definitely it will go through the full of it, the full 4 modules. And again, this is not something that we have access to. We will have access to actually all of the diagnostics before producing the neutrinos, with the protons properties, and then when the particles produced after hitting the targets, then we can actually tweak the horns so that they focus even better, and we'll be able to measure so that we improve on all of this horn business with this 300,000 amps through them. But once the neutrino are produced, this is then very difficult to be able to measure anything on the sides of the beam.
Wow. An issue with some science experiments is that the measurement of the experiment disturbs the thing being measured. Will the detectors affect the flavor or spin of the neutrino?
This is a good question, but they will not. Once the given flavor is there, there will be an interaction, some particle produced through that flavor, and then we'll be able to infer on which flavor it was. In particle physics, we very often work backwards. I compare this with a paintball party, where you just go there after the party and you see a trace of purple paint, and then you see a huge stain of blue paint of something not so fast that were there, and then you see something very, very tiny yellow paint that is spanning the entire field, something very fast were there and leaving the paint. So this is how it works, and this change of flavor is something that happens during the neutrino propagations, and when we detect with a given costume there when we photograph the neutrinos and get the byproducts, let's say in the video, muons and protons, and so then we can infer which flavor was at the origin.
That makes sense. With the large-scale computing you're using, do you use data science techniques like binning and neural net processing in addition to parallel processing?
Oh, yes, this is pretty much what I'm doing with the computing. There are a lot of fancy technique being used at different level, and the parallel processes, this has to be used. So we are actually working on ways to be able to have several units of calculations doing bits of the calculation in parallel and then recombining so that we save time. This is what we call parallel computing farms. Think of it as many units in parallel doing a lot of our many numerous calculations to be able to decide on time, where, for example, you have a trigger decision for a supernova will have to be very, very fast. And there are also other algorithms that are pretty much needed, what we call offline. Once all the data are taken, you have this big pile, it says, okay, lots of pictures of collisions. Then we go from these 2D tracks toward the 3D interactions. Then we use a lot of machine learning algorithm, parts of artificial intelligence, how to find patterns in the data. And this is very computational, so that is also requiring a lot of parallel computing.
What about quantum computing? Can that be used?
Well, we'll have to tell our friends if they want to experiment, but this is something also at its infancy, and the computing infrastructure is planned with classical computing, and this is already a pretty tricky problem to be able to do this. The saying would say, let's try to fit a whale in a bathtub. That's pretty much how big our data is and our current infrastructure. So as we can't change the whale, like poor whale, the data will be the data. There will be terabytes and petabytes of data through DUNE. We increase the bathtub. So we are building a much bigger bathtub, a very robust computing infrastructure to be able to fit the data, analyze and store and transfer, and be able to answer the questions we ask about neutrinos.
Cool. You mentioned that if a supernova were to release neutrinos, it would be detectable at DUNE. Do you guys have to specifically detect a certain region in the sky that you're expecting, or do you measure the whole night sky all at once?
That will be pretty much isotropic in all directions. Basically, we will not care at the beginning. Think of it as we just want to detect a wave, a light perturbation in the whole volume of the detector. And if we detect one here and here and here and here, and then a lot of them are, oh, there is a wave coming in. And this is how the supernovas are going to be detected. Then some algorithms are trying to go back to the directions. If we see the wave coming from here towards us, it's okay, it's there. But if it goes this way, okay, it's there. But this will be an algorithm that will be not favoring any directions of the sky. We would like to catch one, so let's be democratic with all directions so that we get our chance to store a supernova on tape.
Okay. How can you detect the different costumes of neutrinos?
Oh yeah, this is, as I said, with the paintball party, we are basically seeing the different interactions, and we have different processes that are happening, leaving a different signature. So sometimes you will see a very thin track, sometimes you will see a shower, and then you can infer if this was a muon, if this was an electrons. And according to these different patterns, think of it as seeing the tracks and having a library of different patterns that corresponds to different flavor, and then concluding, here there is a muon electron. Okay, that matches a muon electron. So this is based on the topology of these pictures that I showed you in the blue background, where if it's a bit showerish, it's usually some electron signal, and if it's very, very long and thin, this is actually other particles that are hinting on other different interactions that the neutrino can go depending on its flavor while crashing on an atom of argon.
Cool. Will the recent barium vapor released by Kinetic X on May 16th, 2021 tell us anything about neutrino interactions or oscillations?
I didn't get the start of the question, sorry.
Oh, will the recent barium vapor released by Kinetic X on May 16th tell us anything about neutrino interactions or oscillations?
I have to read before answering this question. So I think that I will leave someone expert on this in the comments helping me in that.
Okay. Can DUNE help in the search for dark matter?
Yes and no. There are definitely groups that are going to search for dark matter, and this is going to be done once DUNE will be fully active. And this is a tricky task, but the dark matter, some dark matter experiments are actually made of liquid argon. So at least there is common things in here. But if it's going to be sensitive enough for the dark matter signal, this remains to be studied. There is definitely a team that is going to search for dark matter using the DUNE detector. So stay tuned.
Okay. Do neutrinos travel faster than the speed of light?
No. As soon as an object has a mass, as tiny as it may be, it will always be slower than the speed of light. Always. That is the big speed limitation ruling the entire universe.
Given that the Earth is not perfectly spherical, how will the builders of DUNE point exactly at the far detector?
The Earth is not perfectly round, but we know how not spherical it is. So then there are lots of calculations and GPS system and satellites going to make sure that we are aiming correctly. This is a known. Sort of.
Are you able to collect all the data, or do some measurements need to be thrown out due to the sheer volume?
Very good questions. Actually, we are very economical with the data, because for answering questions about neutrinos, we need an enormous amount of data. And we need the correct data. We do not want to store noise. So what is being on is that at each step, we're going to remove a part of the data that we don't need. If you remember this signal, these bumps on the wires that we're showing on these animations, all of these bumps contain a lot of the data, a lot of wibbles. And so what we are doing is that we clean it up. We just get the bump. That's what we need. And then we'll be able to remove a lot of data, because otherwise it will never fit on the disk. So at each step, we are filtering our data, and we make sure that we only collect what we need for then physics analysis.
So this is it for the questions. Thank you so much.
Welcome.
Back to Elena.
Sorry about that small technical error. Thank you once again, Dr. David. I believe I'm coming through now. And yes, I was so engrossed I almost forgot to unmute my microphone. But this is very, very fun. These very interesting and yet still very antisocial particles. I'm sure everyone will go home with thoughts of these very tiny objects and the gigantic detectors used to find them. So thank you very much for coming over tonight and answering our questions and giving us a wonderful talk. I am going to go ahead and hand over to our president of the Toronto Centre RASC, Tom Luton, to finish off the evening. Take it away, Tom.
Thank you, Elena, and good evening, everybody. I'd like to thank our speaker for a wonderful talk, and let's get into the announcements. So as Elena said earlier, we have two types of meetings here. You've just witness one of our speaker nights, and this is the last speaker night of our season. We take the summer off for the speakers, and we're going to be having only recreational astronomy nights from now until September. If you're here for the first time, please say hello in the YouTube chat, enter some questions for the presenters. If you're a new member, please introduce yourself, and if you're from somewhere far, far away, please let us know where you're from. So our next recreational astronomy night is on Wednesday, the 2nd of June at 7:30 p.m. right here on YouTube. Chris Vaughn will be discussing the sky this month. Stuart Heggie will be talking about astrophotography, deep sky, and skyscapes. And Arushi and Artash Nath will be talking about simulating hypothetical asteroid impact scenarios, learnings from the 2021 Planetary Defense Conference. Online here at YouTube, if you'd like to present something yourself, members, please contact Paul Markov. Turning over to the DDO, DDO Up in the Sky is on Friday, the 21st of May at between 9 and 10:30 p.m. There's a $12.50 fee. You can register online, links at rascto.ca. DDO Ask an Astronomer is on Sunday, the 30th of May from 1 to 2 with Chris Vaughn with a $5.65 fee. Again, links at rascto.ca. Our education and public outreach activities are unfortunately, our in-person events are on hold due to the pandemic. We have and are planning virtual star parties and EPO talks with the Ontario Science Centre, Millennium Square, David Dunlap Observatory, the St. Clair and O'Connor community, the Dunlap Institute, with Brownies, Cubs, Scouts, and school groups, and as well with New Observers to Visual Astronomy. Please contact public education at rascto.ca for more info. Likewise, our outdoor observing sessions at Baby Village Park, at the Long Sault Conservation Area, and the Ontario Science Centre are suspended until further notice. Our club observatory, the Carr Astronomical Observatory near Collingwood, is closed until further notice due to the pandemic. Maintenance activities only are going on up there at the moment. Now, even with things closed down as they are, the Rask Toronto Centre runs on volunteer energy. So if you're a Rask Toronto Centre member, if you're interested in helping, if you've got some free time on your hands, drop us a line at volunteer@rascto.ca. We've got a number of jobs that we are actually actively looking to fill. Our observing committee requires a chair and some new committee members. Our light pollution committee chair is looking for a replacement. We're looking for a national council representative. We're looking for a marketing committee chair and committee members. Our AV committee, who helps put together these wonderful shows, is looking for additional help. EPO is always looking for more folks to help out, especially some telescope and camera operators for upcoming virtual star parties. So please contact volunteer@rascto.ca for more info. Our ongoing Stellarium training courses. Level 1 course for May 31st is unfortunately full, as is the Level 2 course scheduled for June 21st. The Level 3 course, that the date still has to be set yet, is already full. These are popular. We've got a Mobile Plus course coming soon. We've got new trainers coming on board so that we can expand our number of courses. More details are available at rascto.ca/content/stellarium-training-series, and we can add you to waiting lists. The 2021 RASC General Assembly is coming up between June 25th and the 28th. Keynote speaker is going to be Emily Calandrelli, I've mangled that. It's online only, $15 for members and a $20 fee for non-members. The RASC Annual General Meeting is part of the GA. That section of the General Assembly is free to all members. For more details, www.rasc2021ga.ca. This is the part where I get to plug membership in the RASC. You can renew online at secure.rasc.ca. If COVID is finding you in some financial difficulties, we do have an emergency fund for such events. It's completely confidential. Please contact Adela at the national office at mempub@rask.ca for more info. Also, we are selling gift memberships. And with that, I'd like to wish you all a very good night. I'd like to thank you for joining us. If you enjoyed yourself, please come back. You can follow us on the various forms of social media. If you enjoyed what you saw tonight, please like and subscribe and click the notification bell here on YouTube. Be safe, keep looking up, and good evening.